All right, so start the recording. So, what's up? Welcome back.
Hello, hello.
So last time we covered backpropagation, right? And this time, before that, we had covered forward propagation. So now we kind of want to bring everything together. And I don't think I made you do backpropagation enough by hand. Um,
Oh, you made him do it by
so,
hand? Like
well, I
mathematically derive it?
like
No
I
way.
wanted to. I said I didn't do it enough. Um,
Oh,
because that will make you really appreciate what
coding.
JAX is gonna do for you.
Oh,
Um,
okay. Okay.
because you would have to calculate a lot of derivatives in that entire computation graph, if
I
you
think we
remember.
should. I think we should.
So
I think we should
so
just have
that
like a little bonus uh, lecture where we
well,
do it by scratch.
low key, yeah. So uh I want to review backpropagation a little bit, go over some of the shortcomings of ML when you're training your models, so like overfitting regularization.
Mm-hmm.
And then we're gonna be solving um we're gonna be doing two problems. One is a very classical MNIST data set, which I'm sure you've heard about before. It's just a very simple like beginner intro
Very.
to neural networks. And then I'll have you do um a variant of that problem, which is the fashion MNIST, which is the same thing, but instead of numbers, you have like pieces of cloth, basically.
Hmm.
So
Fun fact, that was one of the original projects we did in the first semester of the AI Guild and its founding. I don't know if you remember, Jose. We did
dude, I
MS
need
first,
to
and then
hire
we did a
you.
feminist, ¿cómo se llama? A fashion
We
MS.
did. We
Yeah,
did
yeah. You don't
fashion.
remember? We split into groups, and everybody did their own like thing, and then one group did it on like fashion. Do you not remember that? Or did we all
No.
collectively end up doing? No, we never mind. I'm sorry. We were gonna do fashion, but we ended up doing like an emotion like classifier, like the fate, your face.
Yeah, yeah, that was the build project.
Yeah, yeah.
Yeah.
That was cool.
So, so you already know what I got for you, bro.
Quiz time.
You already know what I got for you, bro. Your finals week starts now.
But Alex, I'm sure you're realizing how important these quizzes are. Like you're definitely being able to see like where are
Yeah.
the holes in your knowledge, right?
Yeah, for sure.
Nice. You got this, brother.
Oh,
Where
I sent
where
the
the stuff
wrong link.
Ay, Dios mío. Things happen.
Wait, I need to edit this with oh no no no. I hope you can hear that. I sent the wrong thing. Okay, go to this. I just sent a link to the slides in the Discord. Sorry. I'll send it in the chat as well here if it's more convenient.
Yeah, I got it.
And
Yeah, I think that's better.
I'll give you some time to go through that. I've made it significantly shorter. I will be giving you 10
Yeah.
minutes though.
I'm gonna put a timer right now.
Okay.
Hey Siri, start a 10-minute timer.
Chill, bro.
Okay,
Chill.
you got 10 minutes.
10 minutes. Starting now.
This is such a good quiz. Even though it's nice and short, but it's such a good quiz.
I'm concentrate,
All right,
bro.
let me shut up.
Okay, I turned it in. I finished.
My dog, ahead of time. You finished in 5 minutes. Let's go over it then. First, if you don't mind, I mean, you're the only person here. You don't mind if I look at your responses, right?
Yeah, of course.
We're violating FERPA right now.
Dude, violating so many codes and this is going on YouTube.
So many student privacy
okay.
laws we're wrecking right now.
What is forward propagation? Okay, forward propagation is when activations are used as inputs for following layers until reaching the output layer to test the accuracy of the model. That's accurate, I'd say. If I were to answer, I mean, can I not? I'm trying to. Can I type?
What?
Oh, I can't answer my own thing. Maybe I'm on edit mode. Published. I think I'm on preview there. Okay, so that is accurate. I would say so. Forward propagation. Also called
The forward
inference, by the way.
Mhm.
You'll often hear it like that. Yeah, or forward pass. But more commonly you'll hear inference. Is as you described. It is
Yep.
how the neural network calculates predictions.
Yep.
Given some inputs. It does this by calculating activations.
Jose, you want me to put another 10 minutes now?
Testing it along.
Track this?
Maybe put 5 minutes.
5 minutes, okay.
So it does it by calculating activation and passing it along to the next layers until you get to the output layer.
And
so that's
Alex, if you don't mind me asking, what is being passed into the activation function?
A linear model.
Yo,
you my dog, bro. You my dog,
Alex. Way to go, bro. Nice.
Yeah, by the way, happy Good Friday, everyone.
Happy
Remember
Good Friday. Yo tenía un versículo que te iba a mandar, by the way. I gotta send it to you later. I gotta send it to you later.
And then so what is backward propagation? Let's see. So backward propagation is an algorithm used to update the weights of each feature by going backwards between the layers. This is how FFNs are trained. I love you, bro. I love you, dog. I just sent you that.
Was that good?
Dog. Yeah, that is pretty good.
Okay.
I would if I would tweak it again, this is just me being
meticulous.
picky. Facts. But it used to update the weights, yes, on each feature. For by going backwards between the layers. So the weights for each neuron.
Nice.
And I guess and on each feature, but the weights correlate to the features. But yeah, just this thing, like for example, this weight 2 Z2 B2, that's like all the weights for all the neurons in that layer, and then this would be all the biases for that. In fact, like if you really think about the activation and the Z here, those are being mainly used as, like they're very important in the forward pass, but in the backward pass, they're mostly used as a way, like we need to take their derivative because of the chain rule, which is what's being done here. But really, the only our model parameters that we're updating is really just the weights and the bias, which is that linear combination. Because the thing is, the linear combination affects these other two. So if you just tweak those, then inherently you're going to change the next two as well. So that makes sense.
Mhm. I got a
It's
follow-up
like
question for you, Alex. Well, actually, I have two. Okay. So
Yeah.
what algorithm is really famous and do we mainly use in backward propagation? It's also used in linear regression so that we best fit the line.
Oh, like the partial derivatives,
Right, but what is the algorithm called? It starts with a G.
gradient descent.
My
Or
boy.
gradient-
My
Would it be
boy.
gradient descent in this case as well?
Yes.
yeah, it
Okay.
still uses gradient descent.
And then the second follow-up question, I don't know if you went over this, Jose, but how many times?
Yeah, 1 second, because of that question you just asked, would we use gradient descent here as well? Remember that the gradient descent algorithm, in fact, the reason why we're calculating these partial derivatives to begin with is so that we are able to perform gradient descent on these parameters. Because gradient descent is pushing us towards the optimal parameters. If you can just think about gradient descent as the way that we update our parameters, it's really just minor tweaks that we're doing on each of the parameters. So we're still doing that. It's just this is a more efficient way to do those little tweaks.
Okay.
That's a good way to think about it, I'd say.
That's a good analogy. Okay, and I don't know if you went over this with them, but how often? So I have two questions. So does back propagation happen after every epoch? Does it happen multiple times? No, you didn't go over.
I don't think I've gone over that terminology.
Okay, don't worry about it. We'll go over it. Soon enough. My bad. I'm getting too excited. I just haven't been in the lecture in a while.
Already know that. I'm sure if you've trained, because you know Relut, so I know you've done a little bit of neural networks before.
Yeah.
So is that something you know about epoch and batches and things like that?
I know epochs, batches. I'm confused about, but I know about epochs.
Okay. So how often does backward propagation happen? Is it after every epoch? Is it after all the epochs are done? And then it does one final back propagation?
Yeah, I'm assuming it's after every epoch.
It's no, it's after every batch.
Every batch?
Yeah.
Okay.
Yeah. I believe when we do like a backward pass where since you do a batch is like you do a lot of calculations. Like you get like as it sounds like a batch, like you grab a couple of training examples, you run forward pass through them, right? And when you go back, what you calculate is like an average loss between all of the ones in the batch.
Okay.
An epoch is one entire run through of the training data. So let's say if I have 1,000 examples and I break it down to 10 batches, so I have 100 examples per batch, then one batch is going to correlate to 100 examples. And so I'm going to, on one epoch, I'm going to do a backward loss 10 times, but I went through the entire data set. So that I'll go over the terminology later on, but good questions.
I'm glad I brought that up. Nice.
So what do we use backpropagation for, and why do we use it? Let's keep violating your code of ethics.
I think we already went over that.
It's used to update model parameters. We use it because it's more efficient. Actually, I'll go over that here on this computation graph. So what's depicted? Yes, there's a computation graph, exactly. And what do we use this for? So this is mainly, I give you the hint. I almost gave you the answer here. The computer needs to be able to efficiently calculate these derivatives and do that layer per layer. So a computation graph is just like an efficient way for us to perform that chain rule going backwards. It's almost like you can think of it like a data structure that we use in order to like efficiently calculate that.
Oh, that's a good analogy, especially for comp sci students. Nice. Oh, you're cooking today, bro. Bravo, chacho.
A Python hoodie. A Python hoodie.
Nice.
So, all right. Now I will give you. I think we're good. I'll give you like 5 minutes for your brain to try to go over this backpropagation refresher, and
Mhm.
then I'll go over the solution right afterwards. So click into that link, and then I'll go over the solution right afterwards.
Okay.
I'll put another 10 minutes, or you want me to put 5?
5.
Hey Siri, put a 5-minute timer.
What's
Minute.
that? That's blank. Yeah. By the way, Alex, I hope you're learning stuff. I hope this stuff is useful.
No, I'm learning a lot.
I feel like people don't come because they're like, well, what's the point? I'm not learning anything here.
And I don't understand how you could not be learning here, to be honest. With the way we go in depth into the material, we certainly didn't do this when I first was learning and Jose first started the AI guild. It definitely wasn't as like foundationally sound, right, Jose? No?
Yeah, bro. Yeah,
Yeah.
it was not. Anyways,
We're
I'll
basically like copying and pasting Coursera, right? For like a good chunk.
it's not like I copy and paste Gemini now. Anyway. Let me know if you want me to like start going over it. I'm low-key doing it with you. So we can. You want a little bit more time, or
No, you could go over it.
okay, chill. Okay, let me delete some of this stuff then. So yeah, quickly going over it. Just wherever it says write code here, write your code there. So we start off with the derivative of the sigmoid function, because that's going to be useful. So as it says there is like, if you take the derivative normally of this function, like you can do this using quotient rule. You can also using power rule if you represent this as
It's the -1.
exactly.
Yeah, that's how I did it.
1 plus e to like the negative z, and then you take this to -1. You know, like you can get that
Yeah.
to be it's the same here. Although you have a negative in front, so you have a -1, then you have a -2, and then you're gonna have like times. And for the sake of the shorthand notation, I'll leave it as e to the negative z. And you can rearrange this, and I will let you validate that, but you can actually rearrange this such that it becomes, you essentially have the same term again, which becomes like your function, your initial function, and then you're gonna have a 1 minus this one, so it becomes like what we have here, s1 minus s. So it's almost like sigmoid times 1 minus sigmoid. So moving on to the next one. Oh, what did I do? Then here, okay, now we're just going to like do our forward pass first, right? Which is fairly simple. So ZH is, if you recall, our pre-activation. I'm gonna do NP dot. You don't really need to do NP dot because they're not really in that format. But you can do NP dot if you want. So, and it's gonna be your features times your weight, right? Plus your bias. And then your activation is just going to be your nonlinear function applied on top of that, which is sigmoid. And that will give you your pre-activation, your activation. And then in the output layer, so your Z out now, which is the pre-activation of the output layer, is, and it's going to be the same thing, but remember that now your input becomes the activation of the previous layer times the weight of that layer plus the bias. All right, just neural networks are not complicated. It's just the same thing over and over again, like a million times. And then your prediction is going to be the same thing, sigmoid applied on top of that. So we understand that pretty well, I'd say. And then for now, for the loss, I'm not gonna take the mean or anything like that. I'm just gonna take like a raw, like y true minus y true minus y prediction, to squared. All right, now back propagation, which is what we're here for. So step 1, gradient with respect to the output layer. Remember, we're going back. So now we're going from output layer all the way to our individual weights and biases. So the first thing that we want to do is calculate the derivative with respect to our loss with respect to our output. That's going to be the first derivative that we use, and this one is going to be quite important. So if you see, our loss here is just this. If we take the derivative of that, we're getting 2 times that, I believe. Right. And sometimes like they want me to put the 0.5 in front so that when you take the derivative, you don't have this 2, like a weird 2. They do like some like mathematical stuff where they'll put 1/2 on here so that when you take this derivative, the 2 and the 1/2 cancel out. I'll leave it here for now for clarity. But we understand this so far. This is just it's just the power rule. And then so now that we've calculated the derivative of our loss with respect to our prediction, okay, now we need to update our final neuron, like the neuron in the last layer, right? Or the neurons in the last layer, in which that's gonna be dy. Right, I gotta speed up here. Z out. So I believe that's going to be the derivative of our sigmoid function, right? Because that's what gave me the derivative of the sigmoid function. And then what I'm passing in there is what I had gotten before, which is this one, right? No. Does it make sense so far?
Yeah.
Actually, I have it.
You have a sigmoid derivative.
Actually, sorry, it's not gonna be that one. It's gonna be y prime. Sorry.
Okay, so just like
Yeah, because it's that's the like you're taking the derivative of y prediction with respect to the output.
okay.
Yeah, it wouldn't make sense for you to pass in to, the result of this derivative. What we're gonna do afterwards is multiply them together. And then you have the derivative with respect to the loss of z out, which is going to be again, like I said, like you multiply these together. So it's gonna be this one multiplied by this one. Whoops. So far. That gives you that one so far. So now we've been able to calculate the loss with respect to the output. Now you can using that, like you can update your gradients there. So now the derivative I think I put it here. The derivative with respect to W out. Sorry, this is where we need to calculate. So the derivative with respect to of the loss with dW out. This one is going to be this last derivative here. Well, did I forget one? Which is the activation? Or no? The oh no. It's not that I forgot to do it. It's just the derivative with respect to it's because you're multiplying essentially like this one is going to be this that we saw before times and it would be this derivative here. But that derivative I'll uncomment this. That's equal to I guess I can put it here. This is BL with respect to these the out, these the well, let me see. It's that when you take the local derivative here, this is what you get. So it's kind of like when you calculate the local derivative here, and it was the prediction with respect to z out. This is going to be z out with respect to the output. And so if we want to calculate the loss of W out with respect to the loss with respect to the out, then it's going to be the loss with respect to this one, and then we need to calculate this z out with respect to W, which is just going to be the activation value. Does that make sense?
Yeah.
It's a little confusing, but and then how much? Okay. And then so we do that for, so again, this is for the bias. I mean the weight. We need to calculate this for the bias. So d out with respect to db out is going to be it's gonna be this times 1, because if you take the derivative of like a variable like b, it's just gonna be 1. On the other hand, you had a coefficient, and that coefficient was this activation. But in this one, you don't have a coefficient. It's just it's just like a constant value. It's just in by itself. Maybe I will do the autocompletes here. I do need to make sure that's, yeah, no, this is wrong.
Jose, just a heads up, for the sake of time, it's already 11:30, all right?
Yeah. Alex, I put the link in the solution. And here you can go through it, but you get the idea. We're just going back. It's like a Russian dollhouse of like derivatives.
Yeah.
But all right,
You
Jaws.
said the solutions were in the slides?
I put
Okay,
I
I
put
see it
this
now.
here.
Yeah.
Yeah.
Okay,
Sorry.
perfect.
I'll give it to Jaws.
Okay. So now we're going to talk about the shortcomings of training ML models and how to address them. One of these problems actually happened in my senior project for a machine learning model that I was doing. But yeah, we'll continue. Next slide, Jose, or do I control it?
Yeah.
Oh, wait. Aren't you going to cover bias variance? And I got, yeah, okay.
Sure, I can cover it.
Yeah,
I can
cover that,
it
and
as
then I'll
well.
do regularization and dropout and stuff.
Okay. So there is, before we can understand like the shortcomings of training neural networks and machine learning models, we first need to understand this thing, bias variance trade-off. So what is this? Why do we care about it? So our model will have these two things, a bias and a variance. And maybe you've heard the term bias before, right? Because we have a parameter called a bias. They're not, I believe they're not exactly related, but the bias here comes from statistics and the variance as well. But essentially a bias is missing the point. So bias is how far your model's predictions are from the true values on average.
Yep.
A high bias means that your model is too simple.
To talk about bias real quick. Just to interject. So yeah, so bias is like something you have to introduce. So in statistics, a lot of the times you're trying to estimate these parameters, which is what we're doing essentially, right? We're estimating each given weight, which is a parameter that is multiplying our are like our input features. Does that make sense? Right? So those things are actual estimators. Now, when you're working with estimation, right? If that is not a perfect estimator or an unbiased estimator, you're going to have some bias, right? And all biases is that when you take whenever you take this thing called an expected operator onto that parameter, and you see that that parameter does not equal the actual parameter that you're trying to get of the actual population, then there's some bias. And essentially all of these neural network models are going to have some sort of bias. Give me one second. Sorry about that, guys.
Good.
Yeah. So yeah, Jose, my bad. I just wanted to introduce some stats in there. You can continue.
Yeah. So the main thing to note here is if your model has a high bias, then it's likely underfitting. Like you have a model that is way too simple. So like you can see that here on this graph with the error. If you have a very high bias, your error is going to be quite large as well, mostly because your model is underfitting. So example, using a straight line to model a curved data, no matter how you position that line, it can capture the underlying pattern of the data, which is nonlinear, right? Variance is the opposite. Your model is all over the place, which likely means that your model is overfitting. So that's essentially like memorizing every single training example rather than learning the underlying distribution. So if you draw, like, let's say you draw a x squared, like quadratic, and then I select different points from that quadratic distribution, and I'm just like drawing a line that passes through all the points. That does not look quadratic. It looks like squiggly lines. That doesn't capture the actual function. So that's overfitting. I actually have some. Okay, so what is the trade-off then? As you decrease the bias, you make your model more complex, and variance typically increases. And as you decrease the variance, your model becomes simpler. So your bias typically increases. So they're a little bit of inversely related. You want your model to be in the sweet spot middle ground where it has the best of variance and bias that optimizes for your error. So again, this is this like optimization problem we've been solving for. So real world analogy, high bias is you consistently miss the target in the same direction. You just need to adjust your aim. So this is like you have like a bow and like you have archery. You're like consistently missing the target, but it's always hitting the same spot. You can, you can see this with like underfitting. If I just have like a linear model, it's gonna be quite predictable. If I have high variance, then your arrows are going all over the place. And you need more consistency. So a good model will have a lower spread, so most of your arrows are hitting in the same place, and they're mostly on target. They're not all over the place. So again, we can see some examples here. So this model is actually underfitting. Because you can see like there's a little bit of like the distribution isn't exactly like linear here. You see it's a bit more like this U-shaped quadratic one. And then the overfitting model is just drawing all these sort of squiggly lines to make room for this particular data set, right? It doesn't actually capture the underlying pattern. So this is the trade-off that you see. If you have high bias and low variance, you're going to get very high prediction error. And if you have high variance and low bias, your error is going to increase in this direction as well. So, okay, I have a question for you, Alex. Does this model capture the underlying trend in the data?
No, because it's overfitting.
Okay, nice. does this model capture the underlying trend in the data?
Like a little bit.
Yeah, like it might be hard to tell
Mm-hmm.
with the simple example, but I'd say no. We still have like a lot of points and things
Okay.
that we're missing.
Yeah.
Does this
And this
capture the
one,
underlying pattern of the
this
data?
one definitely does.
Okay. So this is an example of overfitting, this is underfitting, and this is a good model.
Okay.
I'll skip that. George.
All right, so let's talk a little bit more about overfitting. All right, let's continue to the next slide. All right, so it's very common, as just we went over. There's many ways for you to achieve overfitting, which we're gonna go over in the next couple of slides. But yeah, this is another example. As you can see, that line is basically catching almost like every single point. So it's not going to generalize well to new data. And a good analogy that you can use is that let's say like you're a student and you're prepping for an exam, right? A good student tries to understand all the problems, tries to understand the concepts, so that when they get into a problem that they haven't seen, they understand the concepts well enough that they're able to answer that question. A bad student will just probably memorize the test and perform well on the test. But if it hasn't seen like those questions, right, it's going to perform badly. And that basically is what ends up happening in an overfitting model. In an overfitting model, you're going to train well, right? You're going to have a very low loss in training, but in validation and testing, it's not going to generalize well. Also, if it sees like data that it hasn't seen in the training, for example, in the training data that you're using, it's also going to perform badly as well. So yeah, let's continue. Okay, so how can overfitting occur, right? So let's say if your problem, let's say you have a pretty simple data set, but your model is extremely complex, meaning it has many layers, many neurons. That's one of the ways that it can achieve overfitting. One like machine learning algorithm that we didn't get to go over, but is actually very famous. Sometimes it's very susceptible to overfitting is decision trees, specifically if you don't prune them. Right. Another way that you can overfit is that if you have very like not enough training data. So like if you have, so like in terms of a distribution, right? Imagine with that MNIST data set, if we only had like 2 digits, right? That's a very small like data set, and it would be very easy for the model to overfit on that data, right? It won't really be able to capture the features of each digit well enough, especially if you introduce it a number like 2 where it has some curves and things like that, right? So
it's
imagine
not so much about, sorry to interject, there's not so much about the number of classes that you have. It's not about having 2 numbers.
right.
It's about having like 10 examples for each one. Like, you know, like it's having a low number of examples, not a low number of classes.
Right. Yeah, sorry about that. And then also, if you have like an excessive amount of training, so if you have like way too many epochs, your epochs are way too long, the iterations that you have for each epoch are way too long. And let's take an example with a feed forward neural network. Okay, so if you have too many neurons, this is going to increase training accuracy, because it basically ends up achieving the thing that the bad student did, where it ended up memorizing the data, right? Training too long, yeah, it basically starts to learn initially the features, the edges, the basic shapes of like some sort of image that you're training it on. And as training continues, the weights are going to continue to get adjusted. The smaller gradients are going to minimize the error, but then it's going to stop like generalizing well over those features that it was initially learning, right? Continue. Okay, and how can we combat overfitting and underfitting as well? We have regularization for that. So next. So funnily enough, one of the wait, what? Yeah. I guess I'll introduce it when it comes next. We already went over the bias variance trade-off. We already went over some of the overfitting symptoms. But yeah, basically regularizations are just techniques that penalize the model, right? So that it can improve generalization. right? You want to prevent your model from memorizing your data. That's what you want to do. All right. So let's continue.
So regularization is mainly used to counteract overfitting, by the way. You would counteract underfitting by just making your model more complex.
Yep. Okay, so in here, in my senior project, I basically did linear regression, and my problem with my model is that it had way too much. Like basically, I had a lot of multicollinearity, so I had to use something like ridge regression so that it could penalize the model. I had to introduce a little bit of bias so then it could actually like get the trend of the data as well. So these are very common techniques. L2 regularization, also called ridge regularization or ridge regression, basically ends up adding, if you see that little alpha here, you end up adding some sort
That's a
of
lambda, right?
Isn't that alpha? What?
Which, oh, sorry, you're
Oh,
referencing this
oh,
one.
my bad. I was
looking
looking at last one. My bad. Yeah, sorry.
Sorry, last.
So in
Okay.
ridge, oh, my bad, my bad. So yeah, you end up adding a lambda coefficient, right, to the matrix or the vector of your like parameter of your regressor, right? So once you introduce that, and specifically, it's being added to the diagonal element of that matrix of those regressors, which ends up adding a little bit of bias, and then it ends up removing some of the overfitting qualities that it has, right? Another common technique is lasso regression, which we have right here as an example of lasso regression. And it's actually very similar. So you have like you're multiplying an alpha, you're introducing an alpha where you're multiplying it times the absolute value of the weights itself. And then you can combine these. So there's another way where you have this thing where it's called elastic neck, and you can combine L1 and L2 regularization.
Mm. And by the way, what we're mainly trying to do here is penalize the model from having weights that it just depends on way too much. So it tries to essentially get a more, or like, you penalize the model for having a weight that is very large.
Yep.
So what the model will try to do is like, okay, I'm not gonna make this weight that large then. And maybe it has to use other features in the data set in order to calculate its predictions, meaning you're kind of forcing it to like not just use one thing, like it has to learn other things in the data set too.
Okay, and then another technique is called dropout. So dropout is basically where we change or we drop off some neurons, right? And it could either be in the hidden layer, or optionally you can choose them to be in the input layer as well. So during training, each neuron is assigned some sort of dropout probability, like 0.5, basically saying that there's a 50% chance that the neuron participating in training would like basically be dropped, right? This results in like it ends up changing slightly the architecture, as you can see in the images. You have one fully connected feed forward neural network, and as you can see in the next one, you have some sort of neurons that are like widen out. So basically, they're dropped out, right? Yeah. So this basically is it counteracts overfitting. At test times, when we're testing the data again, you reintroduce these neurons that you initially dropped out, by the way. Okay. So yeah.
Yeah, you just have to multiply by a coefficient that basically, like, if this was like 1/2, like if it was 0.5, like when you do your inference, you might need to multiply your predictions by 2 in order to cancel out
Counteract the
yeah.
0.5. Yep.
So now I want to do a little JAX code along with you. I may not have all the time to go through it fully. But I believe that
We
it
got 15 minutes.
I know. Okay, so it's this one. So I quickly wanted to go over MNS dataset, but using JAX. I don't know. Have you used JAX before?
I used it one time with Gabe and
Okay. Yeah.
one of the group.
So JAX will essentially allow you to all the computation graph and the gradients and all that we were talking about before. It'll just automatically do it for you. It's built on top of an engine called XLA, which stands for Accelerated Linear Algebra. So it will perform all the math computations for you. I'm hoping, yeah. This is just in case we want to use a GPU, but I'm not going to use a GPU in this case. But yeah, the data set that we're going to be using is MNIST. And this is just like loading in the data set, things like that, making one-hot encodings. You know about one-hot encodings, right? No?
No.
Oh, okay, perfect. So if I show you what okay, let me print this out as well. Print, yes, one-hot encoding labels. And then I have, well, I can just print them when we do it. So one-hot matrix. Dog just gave me, by the way, I is the identity matrix, which is return one-hot matrix, and then I also want to print it. Print. Can I print like this? I wonder what that's gonna print. Essentially, I wonder what that's gonna print. Oh, nice. Okay, so, so okay, what does this mean? What does this mean? You may not be able to fully see it here, but essentially we have these 10 classes, right? So the first index here correlates to 1, like it correlates to 0. So like the digit 0, the label 0. And the second one to label 1, so on and so forth, for 0, 1, 2, all the way to 9. Now, if I have a 1 here at the beginning, that indicates that this training example is a 0. All the rest of them are going to be 0. Like all the rest are 0. This means, and one way to interpret this could be, if a neural network is looking at this, and we're using this to calculate, like our true prediction values, right? We're going to contrast this with our output. This should have 100% been a 0. The true value here is 0. So if you're 100% confident that this is a 0, you did very well. If your distribution is a little bit more like, like 50% that it was a 0, 50% that it was a 1, you're a little unsure about that. So essentially, this one-hot encoding, what it allows us to do is like, you just you put a 1 where you have your true prediction, and you put a 0 everywhere else, because all those are not the correct answers, if that makes sense. I have 10 minutes, so I'm gonna quickly go through this. I might need to copy paste some code. Okay, so this is just initializing the network parameters initially to just be random. And yeah, I think I'm sorry, for the sake of time, I am gonna have to copy paste some stuff here. So, okay, what I'm defining here is a forward layer. This should look pretty similar by now. Like this should look fairly intuitive by now. But we have our weights and bias. This activation function here. What you're calculating is the derivative, hyperbolic tangent. It is using 10H as a default, I believe. And so I believe what this will do is, well, actually here we're just defining the forward. We'll define the updates later on. but essentially saying, this is just doing our forward pass. This is essentially a layer forward pass. If we wanted to apply that over all our inputs, then apologies again for copy pasting so much stuff here. But if we wanted to, so this is for a single layer. If we want to do that for the entire network, then what we would do is, so activations here just become our inputs. What we initially pass in, right? It's almost like we initialize activations to the initial inputs. And you apply this for as many layers as you want to have in your network. Using tanh, we can use sigmoid if you want, since that's one that which one is it? Sigmoid. Just keep it as tanh for now. Not entirely sure which other ones they have. Sine, absolute, a cosine. They have a couple. Arcsine, arctangent. They have quite a lot. I'm surprised I don't see. Oh, that's interesting. I'll keep it as tanh for now. Tanh is very similar to sigmoid, if you've seen sigmoid before. They provide like many activation functions. So our activation function can just be tanh. Tanh is very close to sigmoid. So for however many layers we have, we calculate the forward pass for all of them. And then in the last layer, it's going to be a little bit different. When we calculate the activations, they look the same. The only difference is logits is essentially what we're calling the pre-activation of this thing called a softmax. A softmax is a function that we can apply, and I'll cover that next class. We apply this. Have you seen softmax before? No.
Yeah, I've seen it in the guild.
Okay. Softmax, do you remember what it's for?
No.
It essentially converts like an array of numbers into an array of probabilities, right? So if I go back here, if I have my output for my neural network is actually going to be like an array of 10 numbers, right? The array of 10 numbers is telling me like the likelihood of what class this might belong to, because what we're trying to do is identify correctly if this is 0, 1, etc. But they're gonna be all over the place. It's not gonna look this pretty, 1, 0, etc. It's gonna be like I don't know, 0, 0.2, 0.3, 0.1. Like it's gonna be, well, it's actually gonna be worse than that. It's gonna be like -4.5, 2.4, etc. Now we need a way to convert those numbers into probabilities. For that, we use a softmax. I will go over it a little bit more next class, but just know this turns raw numbers, raw activations into probabilities, and that's why we use it. So then of course you want to define your loss function. Here I'm just using, this is an extended version of the cross entropy that we see before. But essentially, remember that the cross entropy was like we went over binary cross entropy. This is I guess you could say like an n-ary cross entropy. It's just like a I can show you later on, but it's like an extended cross entropy. Which remember that comes from like a log likelihood. And then our accuracy, we can take our, by the way, if I'm going too fast, I'm sorry.
You're good.
I have like 4 minutes. We have our predictions from when we calculate the forward pass, which we define here. Again, our forward pass is going to be doing a layer forward for all our layers, and then finally our output layer, which we're doing separately. I think this is intuitive, right? this we've seen. There is a cleaner way of doing this. But I think this is actually a little bit more low level, and I think it actually makes things better to understand. And so for your loss function, we can just take our predictions and then we apply our cross entropy on top of that. And to compute the accuracy, we can take our predictions again, and the predicted classes, and then here we're just calculating like a very simple, okay, on average, how many did we get right? You know, like if we have 10 examples, 9 of them were right, our accuracy is 90%. You know, that's essentially like what we're doing here. For updates, okay, this is where we start to like really get the power of JAX. So we have this grad loss multiplied by our parameters, and well, actually, this is some very interesting notation that we got going on here. But essentially, we want to calculate our gradients, and it's just going to automatically do this for us. Then, I'm sure that you've seen this a million times over by now, but what is this?
That's the like the updating the parameters.
Yeah, this is the gradient descent. Literally, like,
yeah.
This is just gradient descent right here.
Yeah.
JAX is gonna calculate the gradients for us, and we're just going to take those. We unpack them here. I don't know if you've seen this notation before, but it's just like some unpacking. And then finally, to train your neural network, you can I just need to write you can just write a loop that will go over the data and calculate that for you. So you want to shuffle your data first, so that, because at first, like, your data might be like all bucketed into like 0, 1, 2, and 3. You want to shift that around so it's random, so it doesn't consistently like predict the same thing over and over again. And then you want to train in batches. So you take like 100, and then like you send those 100 along, you calculate the gradients, you get the average of those gradients, and you backpropagate using those. I will have to leave. I have a meeting with my manager right now. But yeah, you can go through this. I will post the solution here as well in the slides. But what I would highly recommend you to do is to try it out for yourself in this notebook. Make a copy of it and try it for yourself. Anyways, I gotta stop the recording and I gotta stop everything right now. But yeah.
Right, Jose.